finish my house. Oh, well done. I think it'll take not long.
So I think this is the second last lecture. That is for the evaluation part. So in the two previous lectures, we've talked about statistics methods, especially focusing on descriptive statistics that you can summarize the data you've collected through your user study. And then last time we talked about experimental study, how you design an experiment, and talked about hypothesis testing, independent, dependent variables, and so forth. So today we're going to talk about another group of statistics tools, which is mainly focusing on inferential statistics, which is trying to generalize the finding from your study so that you can make conclusions out of it. So if we recall what we've talked about when we first, in the second previous lecture, about two types of statistic tools. Let's say this is all the population around the world, and we've ran a study with a small sample from them, so each of the dot might represent a person who is using your interface. And you ran a study and you measured something, and the descriptive statistics we talked about in the previous lecture is about summarizing the findings from within that group that you've run the study with. And the tools we are going to study today is based on the findings from your study, how that could be generalized into the whole population, and basically talking about how likely it is that if you make conclusion based on their sample, that's also applicable for the whole population as well. So just to recap, descriptive statistics was all about summarizing the data you've collected. So instead of reporting, like if you had 20 participants, instead of reporting all 20 numbers, you've summarized them into a couple of statistics so that the readers can better understand, having a picture of the overall samples you've collected. So, for example, if you collected error in pixel, like pointing task, and you counted the error in pixels, then you collected 15 errors with 15 participants, let's say, and then how you can summarize it with descriptive statistics is you can report number of samples, you can report what was the mean of the whole measurement, what was the standard deviation, so people can understand what is kind of a distribution of the values that you've collected or measured. Depending on what kind of scale is your measurement, sometimes the mean and standard deviation is the best tool for interval ratio data. But if it's ordinal data such as Likert scale, then it's better to report median, min, max, or IQR, since it cannot be, since the ordinal data, you cannot really assure the difference between each unit is the same. So sometimes it's not fair because they might have been skewed to one direction, having narrower difference between the units on one side of the distribution. And for nominal data, of course, you cannot report mean or median because you cannot really order them. So all you can do is count the number of instances or types, and then you can basically report the frequency, such as there was 6 A's, 8 B's, and 2 C's, and then you can report the mode, which is the most frequent value, or you can do it in a relative way, such as basically reporting the percentage of each of the choices. So that was descriptive statistics, and today we'll be mostly talking about inferential statistics, which is, again, making a prediction about the whole population based on the sample you've ran a user study with. And inferential statistics, the output is pretty much the p-value, which is a probability value of how likely it is you are making type 1 error when you make conclusion based on this sample. So whenever you run inferential statistics, the very basic thing or the very fundamental thing that people are looking at is the p-value, which is a probability of making type 1 error. And we talked about these type 1, type 2 errors when we were talking about hypothesis. So we talked about null and alternative hypothesis, saying it's easier to disprove something rather than proving something based on empirical studies. So instead of setting a hypothesis, once you've set your hypothesis that your design makes difference in terms of user performance or usability, so that's your alternative hypothesis that you want to support, but it's hard to support it or prove it through an empirical study. So you set a null hypothesis, which is an opposite of what you're going to say, and try to find an evidence of how you can reject that. So in this table, the left side or the rows were representing the decision you made based on your study. So if based on the samples, let's say you've collected measurements from 20 people, and then you concluded to reject H0, which means you are going to say there is a difference between the interfaces. And if in reality or in the whole population around the world, if it was the case there was actually no difference with the population, then you're basically making a type 1 error, which is saying your interface is better while it is not really better in the whole population. So that's, in other words, it's called false positive. And the risk of making this type 1 error is usually called alpha level. And this is again the probability level that type 1 error is acceptable. And we also talked about alpha and beta, which is probability of making type 2 error is quite related, but the bottom line that we wanted to remember was scientists are very conservative, so they really don't want to make errors, especially the type 1 errors, saying a certain idea is better than what we've been doing so far. So they want to keep the alpha level as low as possible, and usually in HCI field and many other fields also are having a tolerable sets the alpha level at around 5%, which is 0.05. And then we talked about a little bit about the p-value. When you are testing your hypothesis, you are really measuring the probability of how likely it is that you are making mistake by concluding there is a difference between the interface while there is not really the case. So in essence, today we will be talking about tools that can calculate this p-value depending on different types of user study design. And all you have to do is, based on the p-value that you get out of the inferential statistics, you make conclusions, either you reject H0 or not, and say there is a difference between the conditions or there is not. Before you start statistical analysis, especially doing inferential statistical analysis, it's good to have a feeling of for the data or kind of have an overview of the data. So before you put it into the inferential statistics tools, it's quite useful if you first browse through the data, find if there is any outliers or something it's obvious it's not normal. So maybe some of the samples might have had trouble with the measurement tool so that it had a big spike in one of the samples. Then you can check it if it's an outlier based on the two key fences we've talked about in the previous lecture. And of course you can draw graphs and charts to see if they are the measurements are what you were expecting. So if you draw a chart and all of the measurements were like flat, then there's something wrong. So anyway, so once you've collected the data, it's quite important not before you put it into inferential statistics tools, check them initially so that you don't put garbage into the inferential statistics tool that it will print out garbage data. So one of the important things that you have to check with especially if your measurement is interval ratio data, is to check if the data is normally distributed based on the frequency table. So, and of course, when you plot a frequency distribution table, you can look at the shape of the distribution, if it's a bell curve or not, and then you can subjectively decide if it's normally distributed or not. But there is also a more quantitative tool called Shapiro-Wilk test, where you put your measurements and it will print out a p-value how different it is from the normal distribution. So again, throughout my slides, I won't be talking about the details about how you select menus in SPSS and run different tests, but these yellow sticky notes will have a link to a website which will have a step-by-step guide on using SPSS to run this type of test. So for now, let's say if you ran Shapiro-Wilk test with your measurements, then it will print out the p-value saying how likely it is different from the normal distribution. So if the p-value is higher than 0.05, then you can pretty much say it's not much different from the normal distribution, so it's safe to assume it's normally distributed. But if it's lower than 0.05, then the test is basically saying it's highly likely that your data is different from normal distribution. So the reason why we are emphasizing that you have to check if the data is normally distributed or not is because of depending on if the data is normally distributed or not, you will have to choose different inferential statistics tools. So that's why we are talking about this here. So again, depending on what type of scale is your measurement, and if it's an interval ratio data, if it's normally distributed or not, you basically fall into two categories of inferential statistics tools. One is parametric test, and the other one is non-parametric test. And parametric test is basically called parametric because of, based on the parameters, you can pretty much inference or guess how the samples are distributed. So if you remember, when we were talking about normal distribution, if you give a mean value and the standard deviation, you can pretty much reconstruct the distribution of the sample, right? So given the parameters, which is mean and standard deviation, you can kind of replicate the sample distribution. So that's why it's called parametric test. And of course, this is assuming your data is normally distributed because we are using these parameters of normal distribution. And that's why even if your data is interval ratio, if it's not normally distributed, then you cannot really use parametric test, but you'll have to fall back to non-parametric test.
So this is only for interval ratio.
This is for only interval ratio. So if your data is interval ratio and it's normally distributed, then you can use parametric test. But if it's either an ordinal data or nominal data, or even if it's an interval ratio data, if it's not normally distributed, then you cannot use parametric test because parametric tests are all assuming that you can pretty much reconstruct the sample based on the parameters given, which is mean and standard deviation. So first of all, when you get your data, you check if it's interval ratio. If it is, then check if it's normally distributed, and if it's all of those assumptions, then you can go forward with parametric test. But if it's not, then you'll have to fall back to non-parametric test. That's the bottom line.
Homogeneity variance, is that one that you can correct for? Does that mean?
You can correct for, so it's Levin's test.
So you can still use a parametric test?
Yeah, you can still use the parametric test, and especially in SPSS, it will print out if the homogeneity of variance is met or not, and it will have not only print out the one p-value, single p-value, but it will also print out a couple of p-values that you can correct if the homogeneity of variance is violated. So usually the bottom line should be interval ratio and normally distributed. If it doesn't meet that fall back to non-parametric test, but if it does, then you can safely run parametric test and it will print out other things that if it doesn't miss homogeneous. The variance is not if it's not homogeneous. So we'll first go with the set of parametric tests you can test. And the parametric test pretty much relies on this central limit theorem, which is a concept that when you have a decent number of samples, even though the underlying numbers are quite random, if you take the mean value of them, the mean value will be in distribution of a normal distribution. That's basically a theorem that one of the mathematicians came up with. I don't know who was it. But the reason why this theorem is important in parametric test is that most of the parametric tests are based on this assumption that regardless of the distribution of your samples, if you take a mean value of them, the mean value will be following the normal distribution. So, for example, let's say we are tossing a dice, and what is the probability of seeing one of the sides? Like, let's say, what's the probability of seeing 1 when you toss a dice? 1 out of 6, yes. So each of the sides have 1 out of 6 chance of having up. So as you can see here, if you draw a graph, so this one is when you toss the dice once. So let's say that's 1 sample. When it's a single sample, the probability of seeing the number from 1 to 6 is pretty much the same, right? So it's not normally distributed. But if you think of doing it multiple times and taking the mean value of the outcome, you can easily think that the mean value will be somewhere in between 3 and 4, right? So as you increase the number of samples, the mean value of the observed, or the mean value of the outcome will become normally distributed. So that's basically the central limit theorem, regardless of the distribution of a single observation. If you observe a lot of times, the mean or the average of the observation will become normally distributed. So parametric tests are designed based on this theorem. So that's why it's talking about the mean value and assuming that it's normally distributed, and the mean values become normally distributed when you sample enough number of samples. Then you can compare the mean values of 2 groups, assuming that the mean values will be normally distributed, and in that way, if you sample enough number of samples, then you can pretty much say the mean value I calculate based on this sample will be on the normal distribution, so that we can calculate the probability of how likely is 2 mean values are different or not. So that's the fundamental concept of how parametric tests are designed. So that's why it is important to make sure your sample data is normally distributed before you run parametric test. And depending on your study design or your experimental design, there are different types of parametric tests that you have to choose from. One of the things that you have to look for is, first of all, how many conditions you have in your study. And if you recall what we've talked about in the last lecture, we talked about this concept of independent variable and the levels in the independent variable. So independent variable could be something like a type of interface, and you can have 3 different type of interfaces, which becomes still 1 independent variable, but having 3 levels, right? So if you're comparing group means, which means means of certain groups of 1 independent variable, then depending on the number of levels in there, which means number of conditions within that 1 independent variable, if you have one condition, which we didn't really talk about in the last lecture, but let's say the other two first, and then we'll come back to the one condition. So if you have two conditions you are comparing the mean value of those, then you can pretty much, you will have to run t-test. And if it's more than two conditions, then you'll have to use one of the ANOVA tests. And the other thing that you have to look for is if your user experiment design is either between subject or within subject design. So depending on if it's a between subject design or within subject design, there are two types of t-tests that you'll have to choose from. And if it's between subject design, you'll have to run simple t-test, or sometimes called independent t-test. And if it's within subject design, you'll have to run paired t-test, or sometimes called repeated measure t-test. And we'll see in an example in the next slide why it is important that you choose the right test, because if you choose the wrong test, the conclusion could be totally different. And again, if you have three or more conditions, then you'll have to choose one of the ANOVAs. And again, either your user experiment design was between subject design or within subject design. There are two types of ANOVA tests that you'll have to go with. And if it's between subject design, you'll have to go with simple one-way ANOVA test, or sometimes called independent measure ANOVA test. Or if it's a within subject design, then you'll have to go with repeated measure ANOVA. And the reason why it's called repeated measure is you bring a participant and you measure under one condition, and next time you measure the same participant under another condition, so you repeat different conditions with one participant. So that's why basically it's called repeated measure. And the reason why it's called paired t-test is basically because the two samples or two measurements you've collected from two conditions are paired because of it's from one participant. So that's why it's called paired t-test. So depending number of conditions within, or depending on number of levels within that one independent variable, and depending on if it's within subject or between subject design, you'll have to choose the right test from there. And coming back to this concept of one condition, of course, if you have only one condition, we cannot really say it's a proper or true user experiment. But some of the cases you can actually run inferential statistics even if you have only one condition. So this could be a usability testing. So you are not really comparing two conditions, but you are having only your keyboard. I think the keyboard layout might be a good example. So if you came up with a new keyboard layout and you measured number of characters per minute you can type with your new keyboard layout. The good thing with the keyboard layout is there are some studies already who have measured the average number of characters you can type on a standard keyboard. So instead of having another condition with the standard keyboard and comparing the two things, what you can do is actually measure only the average type speed with your new keyboard layout, but compare it with the standard or well-known measurement that is already known from previous studies. So in that case, you have only one condition that you've done, but you are comparing with a known single number that have been validated with a previous study. So in that case, you can do a one sample t-test for that case. But in most of the cases, when you're running a user experiment in your thesis, it's highly likely you'll have more than one conditions that you compare. So most of the cases you will fall into one of these four tests that is listed here. So once you've run this test, it will pretty much print out a p-value. So how you report in your report is basically saying, based on the p-value that it printed out, you can say either if the conditions are significantly different or not. And depending on the test you run, in addition to the p-value, it will also print out different statistic variables. So, for example, for t-test, it is called t-test because it's using a t distribution or t variable. So if you run the t-test, it will also print out this t value and degree of freedom. The concept of degree of freedom is slightly different between the statistics that you run, but it's pretty much showing you how many number of conditions were there and how many samples you have collected. So when you run a study, the very essential thing or the very basic thing that you have to report is a p-value. But in many cases, it's also recommended to report the statistics variables that the tool you are using. So if it's a t-test, you report the t-statistics with the degree of freedom. And if it's an ANOVA, it's using f-statistics. So you should report that value as well. And the guides that you'll see, let me actually show you one of the guides. If you have internet connection, if you click it, it should open up in a web browser. But for now, let me just open it up manually. So this is one of the links that talks about independent t-test. And it will give you a little bit of background of what that test does. But it will also give you a step-by-step yeah, it has quite a good stuff on it. So I think the reason why I have two yellow stickies on each of the tests is the left one is explaining the concept, and the right one is a step-by-step guide of using SPSS. So this one is not working on this side. I could pretty much copy the link. Copy the link. So should give you kind of an example and a step-by-step procedure which menu you'll have to choose after inputting the data, and for each dialog box what to select and so forth. So and then it will give you what it prints out. So it basically prints out some descriptive statistics, and then it will print out T value here and the degree of freedom, and also should be somewhere a p value.
Let's take showing you the difference between
two conditions, the mean value of two conditions, and also it has a sample of, based on this output, how to write it into a paragraph, which is basically talking about one of the conditions was higher or lower than the other condition. And
so
then
is that t value be a fixed size?
Like one is 2.5 or one times.
For how many metrics you use, or is it just not standardized at all? Like what is it that you mean?
This value is based on, so the inferential statistics are based on different distributions of probability. So even if it's pretty much working on normal distribution, some of the statisticians calculated when you're comparing two mean variables and you give them mean and standard deviation, you can pretty much calculate the probability of the two mean variables being meaningfully different or not. And I think it was called student t-test because the person came up with this t function of calculating this p-value. His last name was student, and I think he named it T function. And this is given the degree of freedom, you can calculate the value of the t function, and then you can compare it with standard t value that should be lower than the table to say that the p-value is significant, or in an essence, I would say it's intermediate procedure to calculate the p-value in the end. So in the end, what we all look at is pretty much the p-value. And it's nothing wrong with just reporting the p-value. But if you report t statistics together, then what the reader can understand is this p-value was based on t-test, first of all. And based on these numbers here, this 38, it also represents, I think the degree of freedom in this case is, pretty sure it's the number of samples minus the number of conditions. So it can tell, the number here can tell how many samples you had and how many conditions you had. And what they can, as making sure there is no error there, what you can actually validate is, given this degree of freedom and this value here, this value is basically based on the sample, but if you have this degree of freedom, there is a table where you can calculate the expected t output, and based on the standard t output and the output that was calculated out of the sample, you can calculate the p-value.
So it really doesn't really tell us too much about the difference between groups. We just know that it's a significant.
Yep, no, so it doesn't tell us much. So in essence, what it is the t statistics. It's an intermediate numbers that will end up calculating the p-value, and this number here will be based on the sample that you've given. So it's always different what numbers you put in, but this degree of freedom will be different based on how many samples you had and how many conditions you had. But this will be all calculated by the statistician, so you don't have to worry about how you calculate those numbers by your hand. So again, it will print out a table. You'll have pretty much the degree of freedom, this column here. So that's 38. That's why it's written here as 38. And 2.428 is this number here, the t number here.
The t value is not the effect size.
It's not the effect size. It's not the effect size. And finally, the p-value is 0.02, might have in another table. Yeah, and then in SPSS, the p-values are usually called significance value. And here you can see it's 0.02, so that's why the report is written as p-value is 0.02. And since it's lower than 0.05, you can say there is a difference between the two groups based on the statistics. So the rest of the test has pretty much the same guideline. It shows you, as an example, what menus you have to select, and then what kind of table you printed out, and which part of the table you have to look at to write a paragraph in your report. So it's up to here. So the main thing that you'll have to worry about is to choose the right statistics method, because once you've chosen a statistics method that's applicable for your case, it's pretty much following that tutorial from using an SPSS, and it will print out the values for yourself, and just your work will be looking at certain values in the table and writing it up in your report. But the main thing that you have to be careful of is choosing the right test that you'll have to run, which is the very first step when you do the analysis. So for example, let's say we ran a within subject experiment, which means each of the participants tried all of the conditions. And we compared two 3D pointing interfaces, A and B, and then you've collected average error in millimeters. And then again, to decide what test you have to do is basically you have to look at two things. First of all, you have to look at what scale it is in. So in this case, it's error in millimeters. It's interval ratio scale. So there's a chance that you can use parametric test, and it's within subject design. So if we go back to the slide here, it's a parametric test, and we have two conditions. So it should be either independent t-test or pair t-test, and we said it was a within subject design. So that gets us to the place where we'll have to run a pair t-test, right? So if you run a pair t-test in SPSS, it will print out the t-statistics and the p-value, and let's say these are the values that it printed out. Then what you can write in your report is participants made significantly less error with interface A because the mean value was 7.2 of errors, and compared to the interface B, which had a mean value of 8.8 of errors. And the reason why this difference is significant is that the p-value was less than 0.05.
If you ran, for example, like you did confidence intervals for means, would you also get a significant result in that?
Should be the same.
Yes,
Should be the same because t-test is basically a summary of interval, significant interval, CI, confidence interval comparison is basically what t-test is doing in a summary. So that's the conclusion you reach. But let's say everything was the same, the measurement was all the same, but let's say if it was actually between subject design, then if you go back to this list here, if it was a between subject design, you should have ran independent t-test instead of pair t-test, right? So if you run if you run the independent t-test with the same sample, it's all those same numbers as we did last time. It's only the test is the difference that you chose the different test. Then the result will be like this. So the p-value will be 0.21, which is not significant. So if you have chosen the wrong test based on misunderstanding what user study design you had, you might reach into totally different conclusions saying there is no significant difference, while in the case it might have had significant difference if you chose the right method. So it is important that you know if your what is your measurement scale is in, and also if it's normally distributed or not, and also if your study design was between subject or within subject, because depending on these parameters, you have to choose the right statistics that you have to run. Sometimes in statistics tool they also print out one-tailed or two-tailed values. Most of the cases you'll be safe to just choose a two-side test or two-tailed t-test, because one-side tests are assuming that you are expecting a direction of the difference, which means you are assuming one interface is better than the other, or one interface is slower than the other, and so forth. While the two-side test or two-tailed test, they are not assuming that such thing, but just focusing on if there is a difference between two or not. And two-tailed tests are more commonly used because this is more conservative, I would say. Another example, what if we have more than two levels in the independent variable, which means we are not comparing two interfaces, but we are actually comparing three options of interfaces. Then if you go back to the slide, this case, we are having 3 or more conditions, so it should be one of the ANOVA tests. And if it's within subject, then you'll have to go with repeated measured ANOVA. If it's between subject design, then you'll have to just go with simple ANOVA or independent measure ANOVA. And in this case, it should be ANOVA, and if it's within subject design, it should be repeated measure ANOVA. If you run the ANOVA test, then it will print out the F statistics and the p-value. And as you can see here, since the p-value is lower than 0.05, you can conclude there was a difference between the 3 conditions. But the problem with ANOVA is the test, it all prints out is the p-value is basically saying there is a difference between the 3 conditions. It's not particularly saying interface A is different from B or A is different from C. So it's not saying the difference in pairs, but it's basically saying there is a difference between the 3. So usually what you do is after you run ANOVA, you have to also run pairwise comparison, because the p-value that ANOVA prints out is it's basically saying there is a difference between the 3, but not making any pair-by-pair comparison. So usually the statistics tool does this automatically. So if you run ANOVA in SPSS, if it prints out the significant p-value, then it will also print out a pairwise comparison, which means comparing each of the pairs. But if it's the case that you'll have to do it manually, then you can do it in a manual way by using pairwise comparison. So, for example, let's say maybe
Post-hoc test.
So post-hoc test means some test that follows a main test.
Yeah, because don't you increase value-wise errors?
Yeah, so that's why we're talking about these corrections. So if you had interface A, B, and C, what ANOVA talks about is if there is a difference between the 3. But we cannot really tell A is better than B or A is better than C in pair. So to reach such conclusion, so if you are happy with just saying there is a difference between 3, then that's fine. You can just report p-value of ANOVA, and then that's the end. But in many cases, what you really want to say is if these 2 are different, or if this is different, or if these are different, or so. So you end up doing a pairwise comparison, comparing A versus B, A versus C, and then B versus C. And as you mentioned about increasing the number of error, so the p-value printed out here, let's say what we are trying to do is to minimize the error under 5% of making a false conclusion, right? But whenever you run a test, what it prints out is the probability of making type 1 error, right? So if the probability of making error here is 0.05, and probability of making error here is 0.05, let's say each of the tests we assume there is a probability of making error of 0.05%, then the probability of making error in total will become 15%, which is you might either make error here or here or here. So the probability of making error in total will become a sum of the whole error that you can make individually. So it will increase the probability of making type 1 error. So when you're doing pairwise comparison, instead of using 0.05 as the standard alpha level, you'll have to correct them into certain lower number so that make the overall error level becomes 0.05. And the typical way you do that is by dividing the alpha level, individual alpha levels, with number of comparison. So if you divide it by 3, then the overall error level will become 0.05. So that's basically what Bonferrini correction is. So when you're doing pairwise comparison, instead of comparing your p-value with the set alpha level of 0.05, you compare it with an alpha level of an alpha level divided by the number of pairs that you have that you are comparing. So if you have 3 conditions, then you can make 3 pairs. So when you're running pairwise comparison, you're basically looking at the p-value, comparing with not 0.05, but 0.167. So in this case, if the p-value is less than 0.167, then you can say there is a difference between this pair or this pair or this pair. So you can easily think that as more the condition there are, this alpha level will significantly go down. So for example, if you have 4 conditions, and if you are wanting to compare pairwisely, then you'll have to divide the alpha level with number of pairs. And if there is 4 conditions, the number of pairs are not 4 but 6. So as the number of conditions increases, the alpha level kind of decreases very fast. So that means if you want to reach certain low alpha level, then you'll have to have more participants, basically.
In that case, would you be better off doing sort of pre-planned contrasts between different groups rather than like all pairwise comparisons?
Yeah, we could do it in that way as well.
I guess it
But-
depends what you've done.
Yeah, it depends on what you think, but for here we are just talking about if there is, if you're going to do a pairwise comparison, you'll have to be careful about the alpha level. Instead of using the conventional one, you'll have to divide it by the number of comparisons. And so that's what Bonferrini correction is basically is. And another statistician came up with a more accurate way of adjusting the alpha level, which is following this equation here. But I think most of the cases, both of the correction prints out pretty much the similar value anyway. So I think Bonferrini correction is more commonly used. Sometimes people use side-up correction as well. But again, in most of the cases, you don't have to do this manually. When you run ANOVA, you can choose what kind of pairwise comparison that you're going to do. And it will basically run the pairwise comparison with the alpha level already adjusted to decrease the overall probability of making errors. So one of the examples here, if you have compared 4 different interfaces, then if you ran ANOVA and it printed out a significant p-value, then the next step would be you want to compare them pairwise. And whenever you look at a pairwise comparison, and if you're doing it manually, then you have to look at the p-value if it's lower than 0.05 divided by the number of comparisons that you are doing. And in this case, if there were 4 conditions, then there will be 6 pairs to compare, and that will make the alpha level 0.0083. And so among the p-values that printed out in all pairs, only the p-values that is lower than 0.008 is the significant results. So far we've talked about assuming there is only one independent variable. And if there is more than one independent variable, we should run another type of inferential statistics. So maybe we can have a 5-minute break now, and then we'll continue from this slide. We'll resume from slide 23. So far we've talked about when there is one independent variable, and could have, even one independent variable could have multiple levels or multiple conditions, more than 2, 3 or 4. But if you have more than one independent variable, then I think in the last lecture we talked about we can not only look at each of the independent variables separately, but could also look at the interaction between them. And for analyzing such results, in SPSS there is a tool called multifactorial ANOVA, or in SPSS this function is called general linear model, which is a more generalized method that does multifactorial ANOVA or n-way ANOVA. So when you have two independent variables, it's the ANOVA that you are looking at is basically two-way ANOVA. So the number that comes before the word way is basically talking about how many independent variables you have. So if it's two-way ANOVA, it's basically talking that you have two independent variables. Sometimes you also call these multifactorial ANOVAs by m by n ANOVA, such as having multiple numbers as a combination of them. And that's why even if you have two independent variables, the number of levels in each independent variable might be different. Like if you remember the table, I think I don't have the table from last time. But anyway, if there were two levels in each of the two independent variables, then it would become 2 by 2 ANOVA. And if it has three levels in one of the independent variables, such as in this table, this graph here. So for gender, there is two levels, male or female. For type of interface, you can have more than two levels, which is in this case 3 levels. Then this becomes 2 by 3 ANOVA or 3 by 2 ANOVA that you are running. And again, this is still two-way ANOVA because we have two independent variables. So this two-way ANOVA, compared to two-way ANOVA, what we've talked before could be called one-way ANOVA because there is only one independent variable. And two-way ANOVA or three or four-way ANOVAs, the main difference between one-way ANOVA is these tests also gives you a p-value not only for the main effects but also the interaction between independent variables. So if you run two-way ANOVA, it will basically print out 3 p-values, one for each of the independent variables, and the third one for the interaction between the two. And this. And you can pretty much write up the conclusion pretty much the same way as you did for one-way ANOVA for each of the main effects, which means if you had two-way ANOVA for this case, and if the p-value was significant in terms of gender, then you can say there was a significant difference between the gender, or if the p-value was significant for the type of interface, then you can say there was a significant difference between the interface and so forth. So those are the main effects. But the interesting thing that we'll have to look at here is the interaction between the two. So, so there are different types of interactions. So let's go with this graph. So if the p-value for the interaction is higher than 0.05, that means basically you are not having interaction between the two independent variables, which means one independent variable is not really affecting the other. So the graph might look like here is the case where you might not see any of the significant effects of the main independent variables also with no interaction. So recalling from this graph here, so if you have two independent variables, the way typically people draw graph is you separate one of the independent variables in different lines. Like here, the gender is different lines, and the type of interface is on the x-axis. So if we go back to this graph, in this case, if you think of if there is a difference between red line and the blue line, then they're quite close with each other. So the p-value might print out very high number, not having difference between the red line and the blue line. But if you also look at the difference between the left and the right side, then again, can see that they are not quite different. So it might print out the p-value that's quite high, so not having significant effect of either of the independent variable. But also here, one independent variable is not really affecting the other, so the interaction might not turn out significant. Compared to that, there are cases where you see significant effects on the main effects, which means each of the independent variable, but not seeing the interaction between them. So, for example, here, the graph here, the red line and the blue line is not much that separate, so you might not see, let's say this is gender, and you might not see that much difference between the gender, but if you compare the left side and the right side, if this is an interface, then you can see there is a significant difference between the interfaces, but not the gender. And the result doesn't really affect the other, so which means either you're male or female, the difference between the interfaces are pretty much has the same effect. The second graph here is showing that the vector B, which is the type of interface, is not having significant difference, but the gender is. So in this case, the blue line and the red line is quite separate, so you will see p-value of significant value. But if you compare the left side and the right side, it's pretty much the same, so it's highly likely you might not see the p-value that's lower than 0.05. And again, independent of being male or female, the effect of the interface is pretty much the same, so there's no interaction here. And the last case here, it's also the red line and the blue lines are quite separate, but also the left side and the right side are quite different. So in this case, you might see significant effect of both of the factors, which means the gender and the interface. But the lines look parallel, which means they are not affecting with each other much. But if there is an interaction, then you might see graphs such as like on this right side that the graphs are not parallel, but they converge on one of the sides of the graph. So, for example, this graph shows that depending on the interface on the left side, it didn't have much difference between the gender, but the interface on the right side, depending on the gender, they had quite different either performance or different effect. And sometimes it could be also, depending on the measurement that you're using, it could also, you could also observe ceiling or floor effects, which means because of the range of the measurement you are having, the results are converging. So let's say this is the Likert scale result for the SUS scale. Then the y-axis becomes the SUS scale ranging from 0 to 100, right? The maximum SUS score you can have is 100. But then you can see there, it looks like as if the gender becomes quite meaningful on the left side of the interface, but on the right side, it looks like the gender doesn't become that much meaningful. But maybe this might be the case because the gender actually has a meaningful effect on the type of interface. But it could be the case that this value here is quite reaching up the maximum value of the SUS level. So if this is quite close to 100, then maybe it's because of the maximum value you're getting from the SUS reading is reaching the highest value, so it's kind of saturating out rather than because of the gender difference. And in the same case, if your reading or the measurements are reaching the minimum value of the possible measurement, then you might be seeing the floor effect where all of the measurements are kind of converging to the minimum value. So those are some of the ways that you can interpret the interaction. One thing you'll have to be careful of is when you see no main effect but seeing the main significant interaction between the two. So this is the case where you might see a graph that looks like this, kind of crossing with each other. So here, if you look at comparing the red line and the blue line, you cannot really say which one is above or lower. And if you compare the left side and the right side, you cannot really say which one is higher or lower. But thus looks like there is a meaningful relationship between the two independent variables, which is crossing with each other. And if you look at the left side independently, definitely there is a difference between the male and female. And if you look at the right side separately, then you can see there is a difference between the gender again. So in this case, you shouldn't conclude straightforward based on the main effects, which means you shouldn't conclude there is no difference between the gender or the interface, but you'll have to report there is a significant interaction between the two, and then you might have to report simple main effects, which means comparing the mean values. It's kind of similar to pairwise comparison that we've talked about before, but in this case, you're grouping them into a certain level in one of the independent variables and comparing the other independent variable within that level. So if you put it into a table here, so let's say this type of interface was one independent variable, and the level of users' expertise was another independent variable. So far, the main effects we were talking about was these blue circles that we were comparing with. The overall difference between novice and expert, and the overall difference between the mouse and touch. But in case of you have significant interaction, you cannot really conclude based on this overall difference between the groups within one independent variable, but you'll have to look into much more coarse or more smaller samples or more or subsets of samples in this case, looking at if there is a difference between mouse and touch when it's novice user, or if there is a difference between mouse and touch if it's an experienced user or an expert. So these are called simple main effects. So once you have a significant interaction, then might be good to have a look at the graph. If the interaction is because of ceiling or floor effect, then maybe you can just report that the significant interaction might have been because of the measurement having certain range. But if the graph does look like crossing with each other, then it's also a good idea that you look into simple main effects, which is basically fixing one of the independent variables value and then looking at the effects of the other independent value within that fixed range. So that's so far what we talked about was parametric test. It was all assuming that the measurement that you've collected are interval ratio data and it's also normally distributed. So basically t-test and ANOVA test and depending on whether it's between subject or within subject design, there were a couple of variants of this t-test and ANOVA test that you have to run. And if your measurement doesn't meet the assumption of the parametric test, which could be the case where your measurement is either ordinal or nominal data, or even if it was interval ratio data, if it doesn't follows the normal distribution, then you have to fall back to non-parametric test. There are kind of similar sets of non-parametric tests that could be kind of one-to-one mapped to the parametric test as well. So let's say if you're testing or comparing ordinal measures such as Likert scale rating or ranking between the interfaces, then if you're comparing two conditions, you can do either man-Whitney U-test or Wilcox and Seinberg test, depending on if your study design is between subject or within subject design. And if you have more than 3 or more conditions, then again there is Kruskal-Wallis test and Friedman test that you can do depending on between subject or within subject design. So if you recall the previous slide on parametric test, these 2 tests are kind of equivalent to t-test in parametric case, and these 2 tests are equivalent to ANOVA test for non-parametric test. So sometimes people call these tests as non-parametric ANOVA test, or these tests as non-parametric t-test equivalent, but it is more formal that you actually call each of the tests based on their own namings, which are basically the names of the people who invented this or came up with this type of test. And again, for Friedman test and Kruskal-Wallis test, again, same as in the case of ANOVA, since all these tests are talking about if there is a difference between the whole group, you'll have to also run post-hoc test by comparing the pairs as well. And in this case, while compared to the parametric test for ANOVA case where the statistics tool did this post-hoc test automatically, not many of the statistics packages does post-hoc test for non-parametric test. So you'll have to do that manually. And in this case, it becomes more important that you make sure you do correction of the alpha level by dividing with the number of pairs that you are comparing, so that you don't increase the overall alpha level in the end. So post-hoc tests are as simple as just running these other 2 tests, which is comparing 2 conditions in pair. So you're basically running first Friedman test and then form pairs of each of the conditions, and then run Wilcoxon-Seinberg test for each of the pairs, but with the alpha level corrected with either Bonferroni or Seidak method. Does that make sense? Sounds a little bit complicated. Yeah, so it's more work, definitely more work with non-parametric test than the parametric test, where with parametric test, the statistics package usually does all these post-hoc test automatically, but if it's non-parametric test, you'll have to run this test separately by yourself. And also you'll have to do the correction of the alpha level by yourself as well. So as an example, let's say it's a between subject experiment and we collected system usability scale, and could argue it could be treated as interval ratio, but let's say this is strictly speaking ordinal data. And you collected these system usability scale from the participants. So it's between subject design and it's ordinal data. So if you go back to this slide of the test, we are comparing 2 conditions. So, and it's a within subject design, so it should be Wilcoxon-Seinberg test we will be running. Oh, sorry, it's between subject design. So it should be man-Whitney U-test we'll be running. So if you run man-Whitney U-test, the reason why it's called man-Whitney U-test is man-Whitney is the 2 person who came up with this test, and the reason why it's called U-test is they have a statistics variable called U. So when you run this man-Whitney U-test, you usually report the U variable together with the P value it prints out. But again, all of the conclusion you make is based on the P value. U is just for a reference that you are using man-Whitney U-test, and even if you don't give P value here, if you just give U value, people can calculate the P value by themselves based on the U value you reported. But anyway, it's kind of a complementary thing that you also report the U value together with the P value. So in your report, what you can say is participants scored interface A significantly lower than interface B, I think, based on the median of each of the samples. And the reason why this difference is significant is because of the p-value it printed out from the MHIT test. So again, so the inferential statistics, all it can say is if the difference is significant or not, but it cannot say which one is higher or lower. The conclusion that you draw here, saying interface A is significantly lower than B, is based on the descriptive statistics, such as in this case, it's based on the median value. So, and for the previous slide, all we have here was assuming there is only one independent variable. But what if there's a case that you have more than one independent variable that you have? And the problem with non-parametric test is it's not actually a problem, but many of the statistics packages doesn't support factorial analysis of non-parametric variables. So, but there are still certain methods such as generalized linear mixed model and generalized estimating equations. I believe generalized linear mixed model, SPSS, does have this function, so you can use this function for analyzing non-parametric tests with more than one independent variable. But there is also another way of dealing with non-parametric data using standard ANOVA procedures, and that's called aligned rank transform, which was invented in 2011, which is relatively new method that is used. And this is the website. I won't go into the details, but what it basically does is once you have your measurements, which is non-parametric, the method they came up with is they developed a tool that you can turn these non-parametric values that will be acceptable for parametric testing. So it's basically based on your raw data, it calculates another set of measurements that meets the requirements of ANOVA test, and then you run the test with the standard ANOVA procedures to get the p-values out of it. So in any case, if your experiments includes more than one independent variable, and if your measurement is non-parametric, then you can choose either one of these tests, either using generalized linear mixed model or using aligned rank transform, which is relatively new method.
Sounds crazy.
Yeah, it sounds crazy. And myself is also not a statistician, so I cannot really explain all the details, but
Yeah, how do you make sure that that rule applies?
yeah, well, so that's the art of statistics, I would say. So again, what I'm saying through this lecture is these are the options that you can choose from depending on your user study design. So the main bottom line is choose the correct method. Otherwise, you might reach into wrong conclusion because of you are using wrong method. So the last type of inferential statistics I would like to talk is tests for nominal dependent variables, which means if you ask them to choose different options, and if you want to say people choose certain option more than the others, then this is the test that you can use. And this is basically chi-square test. Sometimes in the statistics course, they talk about this first before they go into the others, but here I put it the last because this type of non-parametric test for nominal dependent variable. What it basically does is looks into the frequency distribution of the choices and compares it with another set of frequency distribution or expected frequency of distribution. I think it's easier if you go with an example. So we'll talk about an example first and come back to the slide. So let's say in your experiment you had 3 different interfaces, and you ask them to choose the most preferred interface out of them. And then let's say 17 people chose A, 7 people chose B, and 6 people chose C. And what you want to talk here is, it's obvious, or subjectively speaking, it's obvious that people choose A more than the other one. But we want to back up with the statistical evidence that this is meaningful difference between the different interfaces we have. So in this case, since this is nominal data, we use chi-square test, and especially the goodness fit test. What it does is you plot a table with observed frequency of each of the options. So 17 people choose A, 7 people chose B, and 6 people chose C. And then you have another row with an expected choice of, if people chose them randomly, then maybe 10 people might have chose A, 10 people might have chose B, and 10 people might have chose C. And we are comparing these two frequency distribution to see if the choice was meaningful or was it randomly selected. So if you run goodness of fit test, which is a type of chi-square test, it will print out a p-value saying if these two distributions are different or not. So if the p-value is lower than 0.5, you can say these two distributions are different. So the choices they made was not random, but there was another thing that affected their choice, which could be their subjective preference. So that's how the chi-square test works. Depending on so the example we had was comparing with an expected number of samples, right? So you were comparing against a random choice of having each of the options selected equal amount of times. But if you had two different samples, and if you want to compare the distribution between the two, for example, I think, do I have an example for that? Maybe not. I think the example was, if you want to let people choose between two interfaces, and you want to compare it between the gender, if male prefer one interface more than female does, then in that case, you end up with a table like this. So you end up with a table, male, female, interface A, B, C, and let's say 17, 6, 7, and 6, 18, 6. So you can see from the table that looks like female prefers B more, but male prefers A more. And then you want to compare if these two frequency distribution are significantly different or not. And that case is, again, it's still the chi-square test, but slightly different version of chi-square test called test of association or test of independence. But the main difference is, before we were comparing an observed, before the table we had was looking like this, A, B, C, and this was observed. This was random choice. So the main difference between the two is, if you are comparing your observation against certain standard, then it's the chi-square goodness of fit. Otherwise, if you are comparing between the two samples, then it's the test of independence or test of association. So that's what these two options are talking about. So and the catch here is, when you're doing this chi-square test, the chi-square test is expecting to have more than 5 observation in each group. So here, all of the cells were higher than 5, so the chi-square test is applicable. But if you ended up like, if you had 2 small samples and ended up like only 3 in each of the, some of the cells, then the chi-square test might not be applicable and might have to fall back to Fisher exact test. But again, if you use SPSS and do goodness of fit test, it also prints out the Fisher test as well. So it will be easy enough if you use SPSS instead of using them separately in another statistics tool. So in essence, if you're going to compare nominal, if you're going to analyze nominal data output, then chi-square test is what you have to look for. So that's all of the basic inferential statistics that I would like to talk today. So again, this lecture is very superficial. We're not covering whole different types of statistical method in this lecture, but just the common methods that's usually used or widely used in HCI user experiments. And again, I'll kind of wrap up by reminding the limitations of inferential statistics. So all the inferential statistics, the output is a p-value, which is talking about if there is a difference between the group or not. It doesn't talk about how much they are different or which one is higher or lower. For those, you'll have to use descriptive statistics, which is basically reporting mean values or median values or spreadness and so forth, so that you'll have to use both inferential and descriptive statistics together to reach into a conclusion. And again, even if it has a significant difference, it doesn't really means that the difference is meaningful. So a difference being meaningful is not only depending on the numbers, but it also depends on the context, what you are looking at. Again, I think we've talked about this example of difference in test completion time of 400 milliseconds. If it's a task for gaming, then half a second might not be that meaningful. But if it was an interface for driving a car, or if it's an interface for nuclear plant, then half a second could be a meaningful difference. So depending on the task or context or application, statistically significant difference might be meaningful or might not. So in the end, in your paper or in your report, you will be writing a paragraph summarizing these results in your words. So it could be something looking like with one-way repeated measures ANOVA. So you say what kind of statistics tool you used and the alpha level you used. We found a statistically significant difference among 3 interaction methods. So you say how many conditions you were comparing, and then in terms of overall completion time, you're basically talking about independent and dependent variable, and then you were able to say there was a significant difference because of these statistics values. And then if you ran ANOVA with more than 2 conditions, then it's highly likely that you want to compare them pairwise. So the statistics tools such as SPSS might have printed out the post-hoc test doing pairwise comparison, so that you report the further details saying the post-hoc test using 2-kiss HCC. By the way, this is one of the options that you can choose in the SPSS. Showed there was a significant difference only between the touch and hand gesture, but there was no significant difference between other pairs. Then you can talk about participants took more than triple amount of time to complete the task with touch input compared to the hand gesture, because up to this point, all you are saying is there was a difference, but you are not saying which one was faster or slower. So you can add another sentence talking about the descriptive statistics, talking about which one was actually faster or which one was slower. And then you can have a graph of summarizing these results and saying, pointing to the reader to see the graph in figure X. So for each of the dependent variable, you can have a paragraph. So for example, you have the paragraph about test completion time, and then the next paragraph would be talking about position and error that you've measured. And in this case, if you have, in this case, let's say you haven't found any significant difference, so then you can simply report in terms of position error, there was no significant difference between the three interfaces, and that's your conclusion. So that's all for today. The research method in HCI has a chapter about some of the statistical analysis, but I think it's mostly about ANOVA and t-test, none of the non-parametric tests. So if you want to look at more relevant materials, then maybe other books on statistics might be more appropriate. One last thing I would like to point you to is this link here. The link is basically having a big table of a lot of different statistical methods that both we covered today and those I haven't covered today as well. So it's a big table with number of dependent variables, depending on how many dependent variables you have, how many independent variables you have. If the measurement is interval ratio or ordinal, nominal, and if it's an independent group, which means between subject design, and if it's a dependent group, it has a whole lot of different statistical methods that you can choose to compare based on your study design and with different statistical tools. So it might be a good reference when you think your study design doesn't fit into one of the methods that we talked in the lecture, then maybe you can go to this table and look up what other statistical methods you can use. And the other two links in the last slide is the yellow sticky notes I had in the previous slides. Doesn't talk so much about the basics of SPSS, how to type in your variables and so forth. But these two links here at the end of the lecture slide are talking about the basics of SPSS, how to type in your variables and how to input your measurements and so forth. So it might be useful if you read these first and then look at the other methods. Again, to use SPSS, you can remote desktop login to mathlab.canterbury.ac.nz using your UC account. And the next lecture will be on qualitative studies, which will be my last lecture. It will be a little bit less hectic than the previous three lectures. So to wrap up, we'll talk about interviews, focus groups, and other qualitative study methods.